Okay, good afternoon, everyone. 12 o'clock, let's get started. So let me see what people are saying in the chat. How was my weekend? Oh, thank you for asking. It was could have been better. I was sick pretty much the whole weekend. That's why I delayed the practice problems, which I was planning on releasing on Saturday. So my apologies for that. But I was really pretty miserable both days, Saturday and Sunday, and slightly better yesterday, but still, I had to cancel my office hours, and I'm much better today. So hopefully my voice stays, and I will make it to the additional Q&A session that we have planned for tonight, 8 p.m. to 10 p.m. So hopefully my voice serves me well, and I don't lose it um, neither now, neither during the lecture nor during this additional session. So yeah, how was your weekend, folks? What did you do for Halloween? Did you enjoy it? My friends still have unanswered grading inquiries from test 3. Do you know when they will be answered? So is Niha on this call, our head TA? Sometimes she is. If she is not, then I will let her know. Okay, but you feel free to email Niha with this question. So we were supposed to, of course, clear all test 3 grade inquiries. If some of them are still heading, then of course they should be answered. So yeah, I will ask Niha about that. Yeah, it's Compork time. When will we get our homework grades back? Well, homework 4 grades are not going to be done in the next day or two. That's for sure, because we just almost finished grading their test 4, and we will be releasing the grades tonight or tomorrow morning. So that is pretty certain. As for the homework, closer to the end of the week. That's the best estimate I can give you right now. And but we will release homework 4 solutions so that you can look at their solutions and compare them with your answers, and this way prepare yourself better for the upcoming test. Yeah, a lot of people are sick. Yeah, I noticed that too. All right, we should postpone the test. Unfortunately, yeah, I wish I could do that. That would save me from the necessity to write yet another test. You think you are sick and tired of taking the tests? Well, believe me, I'm sick and tired of writing those tests and all the versions and then their makeup test, because every test there are people who had an official excused absence, and we have to write a separate test for them. It's a lot, and of course it's very taxing on our TAs as well. So getting all this grading, TAs and mentors, so it's a lot. And yeah, 7 exams. I'm definitely not enjoying it. So if I knew it would be like that, I would definitely vote for changing this course so that there are fewer exams. But it's too late to do it now, so we have to struggle through this together. So I'll try to make next test, our test on Wednesday tomorrow, not as long as the previous ones. But then that also means do not expect it to have a problem that will be turned into an extra credit. Okay, so we'll probably just have 4 problems, and then all of them will count. All right, and yeah, it's great to see that you enjoyed your Halloween and some of you went home. That's good. All right. Yeah, and then Thanksgiving is just around the corner, and then Christmas. That's I can't tell you how I'm looking forward for the break actually. All right. So the practice problems answers for practice problems for this upcoming test. So I'm going to release them tonight, but with a little twist. So what I noticed is, at least this is my observation, and feel correct me if you think it's wrong. But many people do not actually solve those problems. I know some of you, many of you do, but there is a significant proportion of the people who do not actually solve their problems and just look at the answers. And so to kind of discourage this further, so what I will do, I will release all problems that have answers that you have no other way of checking. So like all their open-ended questions and questions that are not easily checkable, I will release them. Questions that you can check easily, for example, like a conversion problem, you can check yourself easily with there are tons of online tools, and of course you're not going to have access to those tools on the exam, and you don't need to. But to check your answers to practice problems, you can use those tools totally. So I'm not going to be releasing those answers, and I'm not going to be releasing coding problems, solutions to coding problems. Well, maybe I will do one of them, but with a coding problem, it's very easy to verify your answer. Okay, so if your answer you run it in Mars or QtSpim or Spim and it works, then it works. So it's very easy to check. Okay, so that is something that I will try this time, just to sort of reward people who actually do their practice problems the way they are intended to be, to give you problems that you will be solving, not just relying on the answers that are provided. So I think it is fair, but let me know what you think. All right, someone has a DFQ test. Yeah, sorry, it's that time of the year. Tests from all the different classes you're taking. Yeah, we should just not have so many tests. Yeah, I agree. So, initially when when I was planning this course, I just thought we keep the same kind of structure of the syllabus that was in use last semester when another professor was teaching this course, and I thought it would be fine, but I'm not I'm not enjoying it. And since it's in the syllabus, it's kind of late to do this on this next exam, okay, which is tomorrow. So it's something that, well, drop the lowest one. This is something that I'm contemplating. So people who have taken classes with me in the last year or so, they probably know that this is something that I'm usually open to. So this is something that I'm thinking about. Okay, someone says exam every 2 weeks is good. Well, yeah, in some sense it might be because there's very little material, and you don't have a final because we have those frequent exams. So, all right. And I'm just scrolling through the chat. Oh, there's just a lot of. Okay, there's quite a discussion on the answers. Okay, let's do that. I will release all other answers tonight, but then I will release their coding problems tomorrow, so that you still have time to look at it. At the minimum, you all have to attend their lab review, their exam review session during your lab. So you will have 2 hours at least to look at that code, and you will have your lab TAs and mentors to ask questions. Okay. How does that sound? Okay. All right. And let me stop sharing something. Thank you, folks. I'm glad you are reacting positively to this. And let me start sharing something. And let me look at my agenda. All right. So some of the topics we already talked about. Test 4 almost done. Will be released before the next test. Homework 4 is yeah, we haven't really started because everyone was busy doing test 4 grading. And because of that, solutions will be posted. So practice problems for test 5, I already talked about them, and this we already discussed. And so the remaining solutions will be posted, just not tonight, but tomorrow morning. All right, additional Q&A session tonight at 8 o'clock. So not as many people voted for their favorite time as on the previous Q&A session. So only about 30 people roughly, and it looked like the majority of people prefer 8 p.m. tonight. So we will do that this Q&A session, and then let's see how many people show up, and then come back to whether this Q&A session is necessary or not on the next exam. And if you think it's necessary, if there's enough people who think it's necessary closer to the next exam, then as usual, please let me know. I'm open to consider that. And so let me open my chat and Q&A windows. All right, and I can see that Q&A is active. We have our panelists here. Okay, cool. Yeah, and what is on their exam is a question that was answered, and it's even less time. We discussed it during the lecture, and then it was also on the submitted forum. Will we see an exam problem similar to their homework 4 Q8 problem? It is very likely. Of course, you won't be able to do open circuits, but you would need to draw circuits by hand. But there definitely is going to be a question on ALU, right? So we don't have that many topics that we covered, but so essentially it's arithmetic, floating point, and ALU, right? So if we look at the major stuff, so definitely ALU is going to be on the exam. Yeah, drawing circuits. No, well, some people like them actually, more than writing MIPS code, for instance. Flip-flops will be there. No, flip-flops we're going to cover today, and we closed the list of topics for the exam as of the material that we covered last time. Okay. All right. So let me go back. Homework. Well, all right. Yeah. Don't forget that there are also review sessions for the task tomorrow during your lab time slots. Please use that time productively. Please, ask your TAs and mentors questions about their exams, about the practice problems, everything that ask them to draw diagrams. You can make up your own questions, right? So just think about something that you would like, that you think, oh, that might be a question on the exam. How do I do this and that using only and or and not gates, or using only multiplexers, or something like that. So you can make up questions and feed those questions to your lab TAs and mentors, or to submit a forum. That's another good thing. All right. So yeah, I wanted to highlight, please make effective use of their review sessions with your lab TAs and mentors, and that make make good use of them, of your lab TAs and mentors. All right, homework 5 was released, and please start early. This homework looks bigger than your previous homework 4, and I think it is. I think to most of the people, it will take much longer to do this homework 5. It's lots of coding. It's more time consuming than you might think. I don't think an average student would be able to do it in one day, even if you spend like 8 hours. Okay, so I recommend definitely spending, few hours, but over the course of several days, so that you can kind of, think about the code that you will be writing in the background, and not just, sit down and hope to get everything done in like, 8 or even 10 hours. All right. Yeah, I think the code itself is not going to be very hard, but it's going to be a lot of code, right? Because you have to write a parser, then you have to write the actual code that generates MIPS code, and it's going to be probably lots of if else's, to account for all the different cases. Unless you come up with some brilliant idea on how to make this this code more structured, so that it's not just a string of if else's that that has that ifs are nested inside other ifs, nested inside other ifs, and so forth. So that kind of code, of course, is very hard to write and very hard to read. So one other note is please remember that you will have a limited number of submission attempts on Submiti as usual, and we will open Submiti submission page only a couple days before the deadline. So please test everything locally on your machine. Do not rely on Submiti as a debugging tool, because it is not. Okay, and as usual, we're going to have auto-graded parts, and yeah, it's okay if you don't get all the points on your first submission attempt and you need to tweak a few things in your code. It's fine. But if you just start with pretty much empty code, submitted just to see how much points you get initially, and then you add one function and submit another function to submit, then please don't do it. Right? Debug on your own machine. Do not use Submiti for this purpose. Right? Submiti can be slow. Submiti can be overloaded at times. So don't put your submission at risk, please. All right, and yeah, and some of you know that if you get full credit on their first attempt, on your very first submission attempt on Submiti, you get, I think it's confetti, if I'm not mistaken. Okay, yeah. So hopefully, many of you see confetti on homework 5. At least, yeah, it's worth it. I agree. All right, team projects. We're gonna have groups of 4. And the more details will be released at the end of this week, so we probably going to discuss it more on Friday. Okay, so it's coming up. It hasn't been forgotten, but it's not here yet. So let's survive our test 5 and then talk about team projects. And in good news, if you think about it, our test 5 is tomorrow. Our homework 5 has already been released. So what's left is really just 2 exams, 6 and 7, and 2 homework assignments, 6 and 7, and that's it. And then the semester is going to end. And overall, in terms of grades, I think after I released the results of the last lab, I think like over 70 people in the class are at or above the A- threshold. So people are doing well in terms of grades on average. Of course, if you're not one of those 70, you might disagree, but 70 people above A-, at this stage of their class, where we have pretty much half of the points already allocated. I think it's a pretty strong result. And I know this course is hard for many of you, but I think the the results are good. And hopefully you agree that we are grading, that we are grading. Our grading is flexible, and we yeah. Well, not 70% of people, 70 people. I think more than 70. So it's like 35% of the class. Yeah, it's 70 people. Class is like 215 at this point, give or take. I don't remember. I haven't checked recently. Okay. All right. Yeah, it's not 70%. It's 70 people. All right. So let's now go back to our topics then. And first thing that I wanted to talk about, so we need to actually, let's go through these slides and then talk more about their timing diagrams. All right. On. All right, so we talked about matrix multiplication, and so we left off here, and so this is just a reminder. This is something that we already talked about. Right shift and division. So when we do right shift, it is equivalent to division by 2. When we do left shift, it is equivalent to multiplication by 2. Of course, if we shift more than one place, more than one bit, it's equivalent to division or multiplication by the corresponding power of 2. Okay, so the important thing to remember is that this only works for unsigned integers. If we just divide, if we just shift right and fill in their bits on the left with zeros, it only, this only gives their true correct result for unsigned integers. Okay, so for signed integers, we have to do something a little bit more intricate. So if we are performing an arithmetic shift right, we have to replicate the sign bit. Okay, so there are bits that are now vacant and that we have to fill with something. We fill not with 0, but with the sign bit. So here's our -5. Okay, and we are shifting right by 2 positions, and that's why it is right. So there's 2. This 4 is 2 to the power of 2. So we have to use this bit to put into these 2 positions, right? Because as we shift 2 positions to the right, so these 2 bit positions become sort of vacant, and we have to fill them in with something. So we fill them in with the sign bit, not with zeros. And this is what is going to be called arithmetic shift. Remember previously, the shifts that we were talking about, we call them logical, right? And you hopefully remember SLL, shift left logical, shift right logical. So this left stands for logical. And now we have arithmetic shifts, okay, which differ from logical shifts in that they use the sign bit. And of course, this has the special, the special meaning is for the right shift. Okay, because if you're performing a left shift, of course you don't use the sign bit to put in the bits that become vacant on the right. You just fill those with zeros. So for the left shift, it really doesn't matter. There's no difference. But for the right shift, it matters, right? Because we need to select the sign bit to fill in for the most significant bits that are becoming vacant as we are shifting towards the right. Okay, so and this, this arithmetic right shift, if you think about it, it rounds towards -infinity. So, and here is an example. We compare with this, and if we do this shift, you see in programming languages, this is like C and Java, this is three greater signs. Okay, this performs a logical shift, right? So see how it fills their vacant bits with zeros, not with ones. And of course, the result is then interpreted as a positive number, right? So if we interpret this as a negative number, then of course, if you shift right a negative number, you can never have a positive number as the result. So the result would be incorrect if we interpret their operand as a negative number. But if we interpret it as an unsigned, then of course the result is correct. All right, and then associativity. This is another law, right? So we've talked about associativity law with Boolean algebra, and of course you remember the associativity with your regular algebra, and we usually take it for granted. We usually almost do not notice this law. As we are grading your tests and your homework, in many cases, students are not even mentioning associativity, and they combine their use of associativity law with some other laws in one step. Okay, which is not exactly what we were asking you to do, right? We asked you to show each step, even if it's just using a different associativity. Because of the associativity law, you still have to make it a separate step. Okay, and yes, it makes your derivation longer, but it shows each single step with the law that you applied. Well, anyways, so my point here is that we take it for granted. We don't even usually realize that we are using this law. We just combine it with some other steps for simplicity and for speed, so this actually turns out to be a pretty important law, because if you're writing a parallel program, then the order in which operations are executed may matter a whole bunch. So for example, and this is the example that we are shown in the slide, so parallel programs may kind of rearrange operations so in a way that would be completely unexpected for you if you're not experienced enough with parallel programming, if you're not thinking in in 4 dimensions, if you're not considering their time factor, right, or the timing of how operations are performed in time. So if this is the case, then your assumptions of how associativity works may actually fail, because, and this is one other fact that we talked about before, the operations are not atomic. Many operations that you think would be atomic, they're not atomic. And so that means that an operation may be interrupted in the middle and then completed later. All right, so what we have here is we have this operation x plus y plus z. And of course, there are two operations. So there are two ways we can do them. So we can do x plus y and then plus z. Right, this is option number 1. And we can do and we can do y plus z first and then add x. Okay, so this is option number 2. Right, and x and y and z are here. So you can imagine this is like the memory. So you can think of this table as showing the contents of the memory. And here we assume that we can sum values directly in memory and update the results. So x is this, negative 1.5 times 10 to the 38th. Y is the same absolute value as x, but positive, and z is 1.0. So what happens if we are under option 1? Okay, so we add x plus y, and the result is obviously 0. Okay, and so this is our intermediate result. And then we add z, which is 1. and the result is 1. That's pretty straightforward. Okay, so what happens if we change the associativity and our middle school algebra rules says that the result should be the same? Okay, it does not matter which order we perform these plus operations, and it turns out that actually this is not true in digital systems and computer systems, at least with a floating point representation that we're using here. So we first do y plus z. What is y plus z? So this is the result of y plus z. So this is y plus z here. Okay, so it's negative 1.5 times 10 to the 38th. And if we add x and z, okay, and then when we add, if we add, I'm sorry, y plus z. Okay, so their signs are flipped. We're doing y plus z. Oh, y is positive. Yeah, so it's going to be this. Okay, and then it's going to be this. Either way, it doesn't matter, right? So y plus z is 1.5 times 10 to the 38th. And then when we add x, which is negative this, okay, so this is our x, right? This is our y plus z. And when we add them together, we get 0, right? Because they are the exact same absolute value, just different signs. Okay, so and obviously the result is different, and that's the effect of relying on associativity, which, as we see, sometimes fails. Okay, so y is y plus z 1.5 to the 1.5 times 10 to the 38th, right? So I believe this is actually exactly the question that I would like to ask you. Okay, so why doesn't associativity law seem to hold in the slide? Okay, and you have the options. So let me actually open the poll. Okay, and to just give you a hint, spell out this, any of x or y. Well, let's, take y and spell it out with not in a scientific notation, which this is a scientific notation, but just in their, fixed point decimal form. Okay, so it would be something like that, and then add 1.0. Okay, and then represent the result using again their floating point. Okay, so IEEE 754, and so do just the single precision to make things more obvious. Double precision makes things, same problems exist for double precision. It's just they happen with slightly different values. So you're not really solving anything by switching from single to double precision. Yeah, it's not straight math. Exactly. That's the point. Okay, so all right. So that's that, and that brings us to the question of floating point accuracy and why we care about that. And there are many applications when we do care. So scientific code, obviously is important because we can have values that are extremely small, 10 to the negative 300, and extremely large, 10 to the positive, 380. And It also has consequences in finances. So no one would be happy. No customer would be happy if their bank balance is off, even if it's off by a little bit. And yeah, so market is really sensitive to this. And so this slide also mentions a very famous. It was a good number of years ago, but it was in the time of the Pentium processors. But it was a very known division bug. So this FDIV operation had a bug, and it was a huge deal. And Intel had to kind of deal with this problem, and it was a real bug. So it wasn't manifesting itself very often, but it was affecting the accuracy of the division. And there were applications that where it actually mattered, and that's actually how they found out. They didn't find it. They didn't find it until several years after this processor was released. Okay, so and that's why it was a huge fiasco. All right. So, and someone brings up, yes, iPhones had the decimal issue with calculators too. So yeah, it's a big pain in the neck if it happens. So, hopefully you're not gonna make such mistakes when you design your division operation or when you're writing your software. All right. And then we continue our conversation about addition and what we previously talked about. Remember our discussion about half adder, and then we turned it into a full adder that has a carry in and carry out. And we said that it is a ripple carry adder because if we use those single bit adders and combine them into circuits that are capable of adding multiple bit numbers, like a 4-bit adder, 8-bit adder, 32-bit adder, then this carry signal is what actually determines their delay of the entire operation of the entire addition. Because until their carry in signal for their most significant adder is computed correctly, the entire result cannot be assumed to be correct. And no, this slide is it's just an animation, right? It shows you that addition can be slow if you use a ripple carry approach. So it's just for funsies. All right. So to understand why ripple carry is slow to begin with, we have to think about what this way of making an adder, how it works. So each 1-bit adder, and in our case 1-bit adder was part of a 1-bit ALU, has several levels of gates, and the input to their ith ALU includes an output from their I-1th ALU. So in other words, if we draw a very crude diagram, right, we can depict it like that. So this is our ALU 0, and this is our ALU 31, and the input to ALU 31, or one of the inputs, depends on the output of ALU 30. That depends on the output of ALU 29, and so forth, all the way to ALU 0. And each ALU has a certain delay, has a latency, right? No electronic circuit can switch the outputs in 0 time, immediately, instantaneously. So there is always a delay. And that means that from the time we supply inputs to our ALU 0 until their outputs are all established, are all set to correct levels for this ALU 0, there is a finite amount of time. And then, of course, we should count that our ALU 1 will start making its own correct outputs only from the time when it gets all the correct inputs established. Okay, so whatever was done previously, it's not those were not valid inputs yet. So whatever ALU1 results were, they were not valid either. But from the time all valid inputs are supplied to ALU1, that's when we count our latency, and latency seconds later, we know that ALU1 has all the correct outputs set up, and so forth. So you see that it's like a chain, and therefore, of course, the more bits you want to have combined in such a manner, the more the delay is going to be. Okay, so yeah, let's actually look at some examples, or try to build such an example. And of course, we need to talk about now timing diagrams and delays. So it's a little bit deeper into the computer engineering, electrical engineering side of things, but it is worth it because it allows you to understand what really is going on inside those circuits. All right, and so let's take an input and use an output and have a gate and have another input. And then let's have another gate. And I'm making the circuit very simple, trivial on purpose so that we can actually look at what is going on here. All right, hopefully I am done. Okay, so that's not the LED that I want. I want just a simple LED, which is this. Okay, so this is not open circuits. This is a simulator called Circuit Verse. And the reason I use it for this demo is because it actually allows you to look at the waveform, at the timing diagram, which open circuits does not yet is not yet capable of doing. So, what I also need to do here. All right, let's switch their values, and so I switch this to 1, and I switch this to 1, and I can see that actually. Do this and just flip it. All right, so we see that this works, but now I'm interested in looking at the timing diagram. So how fast does this circuit switch? So what is the amount of time that passes from the time I switch, I flip one of their inputs until their LED reacts and turns itself on or turns itself off? So that's really the question that we need to be looking at. And if you look at the gates, there is a programmable parameter called delay. So it's 10 and 10, but we can of course make it different. Okay, but then like how do we actually measure it? And we can look at so there is a component called flag right here that we can actually look at and I can make it a little bit bigger. So you can see F1 is my flag. and now it's at 0. So it's basically like an oscilloscope view. And if I flip, I can see that, yes, my output switched from 0 to 1. I see this rising edge. This is called a rising edge here. And so I can actually observe everything the way it works. And let me add another flag. So I will call this F1, and then I will add another flag F2 here. And now I can see both of them. Okay, and so if I switch this off, I can see, and let me pause my diagram, and let's see if I can zoom in. Okay, zoom in. No, I want to. One. You reset it. Okay, I know why it's zoom stop. Right, so their idea is, and maybe let me download it as an image and then just open it. Okay, so you can see that there is clearly, a shift in time. So time is my x-axis, and you see that from their change in the input signal to their change in the output signal, there is this delay, there is this latency. Okay, and that latency is determined by their delay of their gates, right? From the time my input switches on this for this first AND gate until the output of this gate switches to the correct state corresponding to the new input. There is 10 whatever units this simulator is using, right? 10 milliseconds, 10 nanoseconds, it doesn't matter, right? 10 time units. And then from this time, their input to this second gate is now in the correct state. And we have to measure 10 more time units until the output of this second AND gate is now correct. Okay, and so if we increase their delay, let's do 50 the first and 50 for the second. Typically, the same gates, of course, would have the same latency, the same delay, right? And now let's reset our timing diagram, and let's auto calibrate, and then switch from 0 to 1. And you see that, the delay is much longer, right? You see here the delay is huge, right? That is because my gates are now much slower than they used to be. All right, so that's the idea of their speed of pretty much any electronic components. All right, and so now let's, and someone suggested in the chat, I think I've seen this scroll by, that, well, we can actually connect to the clock and, instead of clicking the buttons ourselves, and we can do it that way. So let me save my current project offline, save offline. Okay, and I think I just okay, and this is the one that we just created. All right, so it accidentally overwrote the other design that I wanted to show you, but it's not a big problem. And but this circuit-verse system is a little less convenient than open circuits because it does not allow you to actually save their circuits as files. It saves it in their browser storage. So, and if you look at their examples that I shared with you, you have one of those files, circuitverse.org, clocked and .txt. So this is the circuit that I'm about to show you. And yeah, I overwrote it. I had it saved, but it's not a big deal because I have it backed up in this file. So, and if we open it, you will see what it is. So it's just a JSON file inside, and we can actually move it into our browser, local browser storage. And for that, I had to install a plugin for my Chrome called Local Storage Manager. And here I have my circuit. Here it is. And this is the ID of the circuit. So now I just need to load it in and find it. All right, here it is. And name clocked and okay. And then I'm going to remove it. And then I'm going to add it. So the key is this, and then the value. I need to grab this part, but I need to get rid of all the escaping. So I will replace those with just straight double quotes. Okay, and I believe that should, oops, I need their braces as well. So hopefully that does it. And let's see. And I project and open offline and clocked and project. Yes, and it did load the project that I just copied from the file that I shared with you. All right, so you hopefully can do the same thing. And now here I have an AND gate, and I also have a clock. Here's the clock, and if you look at the clock, come on, clock. All right, here's the clock. So the clock time, which is basically the period, is 1 second, 1,000 milliseconds, and I can change that. And so I have an additional component that is called a counter, and that counter, as you can imagine, it counts. So whenever it receives an edge, whenever there is a change of the state from 0 to 1 on this clock input, it changes their output value. And it's a 1-bit clock, so obviously the only two output values are 0 and 1. So imagine initially it was in the state of 0, and let me actually disconnect this clock for now and just have something simple as a button. connected here. Okay, and then let me. All right, so you see now it's at 0, and when I toggle the button, it switches to 1. And when I toggle the button, it switches to 0. Toggle the button, it switches to 1. So it counts the number of pulses that I'm feeding on this clock input. Okay, so let me reconnect the clock. And now in the timing diagram, or set the timing diagram, I should see the result of the counter. Okay, and let me know why it's refusing to pause, but we can actually stop the simulation and yeah, just disable the clock for now. Okay, just kind of freeze. All right, so let's look at the timing diagram. So F1 is our clock, and we see that it switches from 0 to 1, from 1 to 0. This is just the clock, and then our F2 is the output of this single bit counter. And as you can see, yes, there is a significant delay. And let me grab this as another image so that I can draw on it. Okay, let me enable the clock. Okay, and then I'm just going to do a screenshot so that I can draw on it. All right, so what do we see here? Right, and I will need to be switching back and forth. So F1 is my clock, and as you can see, every rising edge of the clock causes the change in their counter output. Right, so you see, and in timing diagrams, we show dependencies by drawing arrows. So it means that this rising edge causes this counter output value to go from 1 to 0. And then next edge causes this edge, and then the next rising edge of the clock is this. So you see, it is periodical. It is periodic, and but the period is different from the period of the clock. This is the period of the clock. Okay, and we know from the simulation parameters that it is 1,000 milliseconds or 1 second. And we see if we look at the period of course, all right. So this is the period of the signal at the output of the clock. So what is that period? Can someone tell me in milliseconds? Exactly, it is 2000 milliseconds. It is twice. So we see that a single bit counter actually works as a frequency divider. Okay, the clock, we can treat F2 as a clock with a frequency half the frequency of F1, and it's because it's a 1-bit divider. Can someone tell me if we have a 2-bit divider, by which factor is it going to be dividing the frequency? So if we have a 2-bit divider, so it's going to be F1, F2, So F1 is 100%. F2 would be greater or smaller? It's going to be smaller, right? The frequency will be smaller. And by which factor? By a factor of 4, exactly. So F2 will be 1/4 of F1. So if we say F1 is 1, then F2 would be 1/4. Okay, so that's that's very useful actually. And then we see that as someone noted, there is a delay, and I made this delay pretty pretty sizable, right? So the delay is, or latency is this, right? So from here to here, and we can go back and actually look at their delay and look at their parameters, and the delay is 10 here, and so there is a delay of 10 here for the AND gate. Okay, so and then their AND gate gets the original clock and the divided clock, right? The clock that runs at half the frequency as its inputs. So obviously the output, which is F3, is going to be 1 only when both the original clock and our half frequency, our divided clock, are 1. And this is exactly what we see in their diagram. So when our clocks are both high, and let me just use a different color. Right? High and high. And with the delay, we see the output that is high. And then high and high. And with the delay, we see that their output is high, right? So we can kind of draw those arrows. So when both inputs are 1, with some delay, the output switches to 1. And when any of their inputs switches to 0, or if both of them are 0, of course, our output switches to 0 as well, because it's an AND gate. Okay, so that's the significance of delays, and that's how you analyze and draw timing diagrams. Someone is asking if it's going to be on their exam, and the answer is absolutely, it is going to be on the exam, just not on this one, but on their following one, right? And just for fun, let's see if the simulator actually allows 0 delays, which of course is not realistic, but let's see if it worked. I think it did. Okay, and now we see this idealistic picture, which we're never going to see in the real life, right? When their latency is 0. But now you can see, oh yeah, it's all aligned, right? Because there are no delays. Okay, but in real circuits, there are always delays. All right, so that was that. You scared me for a second. I was just kidding. Hopefully, I'm not that scared. All right. So one question I have for you: if I ask, so I was deliberately vague about how we implement this counter. Okay. So I told you what it does. I told you how it works. We saw in a simulated circuit how it actually works. Right. It just counts their rising edges that it receives at this clock input. But if I asked you to implement it, what would be your approach? Any thoughts? rest it in Minecraft. That's a good answer. But in general, so if I only told you to use the things that we covered so far, so like all the gates, all their multiplexers, all their decoders, and whatnot, do you think you would be able to implement this counter, or something is missing, and you would tell me, well, this is not enough. I cannot make this counter out of the components that we've covered so far. And if so, why? What is the fundamental thing? Well, you can't really count it because if you use something to remember what it was counted, a brilliant answer, right? The keyword here is remember or memory. Exactly. You cannot do this counter without the memory because remember, the circuits that we've covered so far, they were very simple. We have some inputs, we have some gates, okay, and then we have some outputs, and outputs always reflect the state of the inputs. Yes, gates have delays, so the output will be delayed with respect to the inputs, but it's purely a function. Okay, so there is no memory in those circuits. They do not have a state. Their state is always the direct reflection of the inputs, and those circuits are called combinational circuits. And then, that brings us to the question, well, we cannot do a whole lot with just combinational circuits because for things like this counter, right, it needs to remember its current state so that when the next pulse comes, it knows that it needs to kind of add 1 to it, okay, and switch to their next state. All right, so it needs some memory, and this is something that we will talk about a little bit later today. So we first finish with their carry-lookahead, and then we'll go back to the topic of memory, and that would complete our chapter 3. All right, so let's go back to our slides. And so we started with just a general observation that ripple carry is slow, and what I strongly encourage you to do, and I'm pretty sure you're gonna pat yourself on the back if you do this, and it might help you on the future test. So look at the ripple carry circuit that we previously looked at. Okay, and let me find it for you in our textbook. All right, and where is it? All right, so this is our adder. Okay, this is the full adder, and you can see that, well, there are 2 levels of gates. So if I told you that, assume that both the AND and the OR gates have the same latency, let's say 10 milliseconds, then from the time we supply the correct value of carry in to the time when this adder produces the correct carry out signal, how long is it going to take? And the answer is 20, right? Because it's 10 plus 10. We have 2 levels of gates. So if each introduces latency of 10, then it's 20. It doesn't matter that we have 3 gates at this first level because they all kind of work in parallel, right? They are connected in parallel, as you can see. So the delay would be 20 milliseconds or nanoseconds, whatever that the unit might be. It doesn't really. Of course, it's important for the real circuit, but for our analysis, it's 20 time units, whatever that unit is. All right. So now imagine that you are chaining your adders like that. So you carry in into ALU0, causes this carry out from ALU0 to be correctly computed at most 20 time units later. Okay, and then ALU1 will only have the correct output on its own carry out pin 20 time units after it received the correct value of the carry in. So you see how each ALU unit, the single bit ALU unit, will be introducing a 20 time unit latency into the processing of carry signal. And of course, the total delay is the total latency is going to be 20 times 32, right? In this case, and of course, you have this is the full circuit. Okay, so you see that things are if we are not just having adders, right? That was the adder, but if we are having ALUs, right? It adds a couple more components. So the adder is for the carry out signal. Is only adder that is involved, right? Carry in goes into the adder, carry out leaves the adder. But as far as the final result is concerned, we also have to add the delay or latency of this multiplexer. Okay, so imagine that carry in into our most significant ALU arrives at time 20 times 31 time units, and then the carry out from the most significant bit doesn't really matter, right? It will be used for the overflow signal, but not for the result. But for the result, we need to add the latency inside the adder, which would be just 2 gates, all right? So 20 in our example, plus whatever the latency of the multiplexer is. And as you remember, multiplexer we can think of just as a bunch of gates. So we can implement a multiplexer with gates. So you need to look at the internals of the multiplexer to count what is the latency from the time when operation, which is the select signal, is supplied and all inputs are supplied until the result is correct. And so this latency thing, it's important to remember that it is the maximum value guaranteed by the manufacturer of the IC. Okay, and so your actual outputs may be ready earlier than that, earlier than 20 milliseconds in our or 20 time units in our example, but it is the worst case. It is the maximum amount of time, and of course, in our analysis, we have to be conservative. We have to account for the worst case when each gate is introducing exactly 10 time units. All right, we cannot be optimistic in this case. All right, so that's that, and yeah, just be ready to reason about latencies, especially in compound circuits like this 32-bit ALU. And we are going back to here. So, and of course, it's very slow, right? So if we look at our 32-bit ALU, then basically the latency is the latency of one ALU times 32, roughly. Okay, it's way too slow. And what can we do to make things better? Well, one, we can, instead of using our single bit ALUs and chaining them, their output of one to their input of another, we could just treat our 32-bit ALU as a single Boolean function, okay, or as 32 Boolean functions, one function for each bit of the result, and then make a truth table, do our K-map. Of course, K-map for that many variables would not be realistic, but use some other method of minimization and produce the truth table, and then use POS or SOP and code, just encode this truth table in hardware using just gates. That would be, of course, a lot faster implementation, but the price that we would have to pay is it's going to be a lot more complicated. It's going to have a lot more gates, too much hardware, too expensive for most scenarios. So there's got to be something else, and there is. A more efficient approach is designing a so-called carry-lookahead unit. And what it means is, well, we analyze the problem that we have on hand, and that is the ripple. So the problem that we have one carry signal that takes a very long time to propagate because it has to propagate through all the single bit ALUs, right? So of course the worst is going to be for the most significant bit because it would have to wait for carry in to go through all other single bit ALUs. And what we can try doing is computing those carry in bits faster by just using an approach similar to truth tables, right? But just computing those carry in signals separately and faster. And it would still not be constant time, unfortunately, but it will. But it is going to be leaps and bounds faster than ripple carry. And so here's our analysis of carry in and the basically the truth table. Okay, so we have A and B, our operands of the summation. This is the carry in, this is the carry out, and this sum is the result. Okay, and if we look at this table, we can see that, interesting. So carry out I minus 1 is actually connected to carry in 1 for I greater than 1. And we know how to compute those carry outs from the truth table. Okay, so maybe we can do this, right? So carry in 0, carry in not is just an input to the error. There's nothing we can do about it, right? So we don't compute this, it's an input. But carry in 1, okay, so this is their incoming carry into ALU or adder 1, and it is actually a function of A naught, B naught, and carry in 0, because this carry in 1 is actually carry out 0, right? So what comes out of carry out in ALU 0 goes into carry in for ALU 1. So, and this carry out 0 is a function of inputs A0, B0, and carry in 0. So we can write carry in 1, and it's this, right? So, and this is a sum of products, and it just gets, we just get it directly from the truth table. And note that as any SOP, it's just 2 levels of gates. So if each gate is, let's say, 10 time units latency, introduces a latency of 10 time units, then the worst we can get here is 20. Okay, so that's the idea. And then what about the next carry in 2? Well, we use the same approach. Okay, so it's B1 times carry in 1 times A1 times carry in 1. So it doesn't seem like any kind of improvement, but it really is, because carry in 1, this thing we have already computed, right? It's this whole expression for carry in 1. So we can substitute carry in 1 here and obtain a single expression for carry in 2. And it's an SOP, so it is still a sum of product, and therefore it's only 2 levels of gates. So to compute carry in 2, all of a sudden we don't need 40 milliseconds, whatever the time unit is. We only need 20. Okay, and then we can do the same for carry in 3, carry in 4, and so forth, all the way to carry in 31, and we will see that that constant constant latency, which is great. However, there is one downside, and it's right here. The length of these expressions, it gets way too big, way too fast. In other words, for carry in 1, it's not too bad, but if you keep substituting, can you imagine your carry in 31? It's going to be a monster, and that's why that this approach looks attractive, but it's not really it's not really too practical. So we can still, we don't have to give up on this idea, but we can describe our carry in a slightly different manner. All right. So this is our expression for the general I plus first carry in. Okay, and this is the formula that we've seen before. So how else can we describe it? And this is your next pop quiz. We can describe it by rearranging this expression so that we isolate CI. And then it turns out we can do something useful with it. And let's do our second lecture poll for today. Okay, done. All right, so this is your pop quiz. This is your sub-mini poll, and we are moving on to this idea. So we assume we can isolate, and this is how we do that, right? So now CI plus 1 is a function of AI, BI, and also CI. And when we rearrange this, we see these two terms that we can even give them their own names. Generate and propagate. Okay, so we just give shorter names to this product and this sum. And if we do that, then we can so this is initially just a notational thing. So we just introduce this notation that allows us to write this formula slightly shorter. So that CI plus 1 is GI generate I plus propagate I times CI. But if we look at it a little bit deeper, we can actually see that it's not just a notation thing. It's actually meaningful. And if we look at, I like this approach that that our textbook uses to demonstrate the concept with plumbing. And when we go over test 4 results, I actually prepared a similar diagram for question 6 on our previous test to make it hopefully appealing and to help you folks easier understand what the question 6 answer was supposed to be. Right. So try to find analogies that appeal to you when things are not very clear. If you just think about gates and electric signals, try to find an analogy that that is more appealing to you. So here is the analogy for our generate and propagate. So imagine that we have a pipe, okay, which is actually how the electric how the electric signals propagate. Here it's water or whatever your fluid is. Okay, and so this is C0, this is incoming carry, and then you can treat each G and P as a valve. Okay, so P allows the water to flow down to propagate, that's why it's called propagate, and G is a source of new water, is a generate. So we can see that if we have those valves and wrenches to make those turn those valves closed or open. So if I'm looking at C2, there's going to be water at C2 here at the end of our pipe. When? Well, either there is water from C0 and both P0 and P1 are open, or G0 is open and P1 is open, so that we have this water from G0 going into the pipe, and then if P1 is open, the water would flow down to C2. Or G1 is open, and that's the only condition, right? The water is generated here. There are no more valves down the line. So if G1 is open, C2 is going to see water flowing out of the pipe. Okay, so that's the analogy. So P propagate says that our carry signal or the water is allowed to propagate, and if all the consecutive P valves or P signals allow the water, the carry, to propagate, we're going to see that that carry signal at the end of our pipe at the output. Or there are other alternatives. If in any of those sections of the pipe the water is generated and the corresponding valve, G valve, is open, then of course the water, might enter the pipe at any of those segments. And to make this analogy complete, each segment is like a 1-bit adder or a 1-bit ALU. Okay, so I find this analogy very very helpful. I don't know if you agree, but let's move on. And so now we can, using this notation, G and P, generate and propagate, we can rewrite our functions as follows. So carry at I plus first would be 1 if either carry is generated at 1, so it's like this, G, I, so generate, right, water added at segment I, or water was incoming into this segment, so CI is the incoming carry, and the valve is open, this P valve, propagate valve, is open, and it allows this water to propagate down the pipe. And GI and PI we already discussed in the previous slide. Those are just the and the or of the corresponding inputs. So both AI and BI must be 1 for GI to become 1, right? Because in order to generate the carry, we need to have 1 and 1, right? We know that's when the carry will be generated, right? Because it's going to be 0 and there's going to be 1 carry. This is to generate the carry. As for the propagation of the carry, we know that even if we have 0 and 1 and there is an incoming carry, then there will be an outgoing carry if either this or this is 1. Okay, so there are combinations 0, 1 or 1, 0. If there is an incoming carry, then there will be an outgoing carry as well. So to propagate the carry, we need one of A or B to be true, to be 1, and then the carry, the incoming carry, will be propagated. All right, so using this notation, so that was actually the hardest part, the hardest part, right? So now it's just, doing the substitutions with this new notation using G's and P's. So obviously for C1, we have the incoming carry, and it is allowed to propagate, or we have the carry generated in the first least significant bit. Okay, so that's the expression. And then for C2, we just write it as this general form. It's the same form as above, just with the proper indices. Note that, if index is 1 here, here, and here, it's 0. So if it's 2 here, then it's 1, 1, and 1 here. And then we perform our substitutions. So G1 and P1, they're not going to change, but C1, right? So C1 is this. So we substitute this for C1, all right? This is our C1, okay? And then we simplify. Remember, all those algebraic transformations of Boolean functions, they come pretty handy, right? So we simplify this into this, and then we do the same for C3, C4, and so forth. All right, so, and as you can see, as we move forward with this, so for C4, you should still be able to write this out, but of course for subsequent bits, it's getting progressively harder. It's going to be, too hard to compute still. So, but the idea is worthy. So what is the proposed solution? The proposed solution is, instead of doing this for all C's from C1 all the way to C30 first, make them into smaller groups, let's say of 4 bits, to keep things under control. Like we can see on the slide, for 4 bits, it's manageable. And then combine those groups of 4, the computation for carry flags, carry signals for groups of 4, so that, in a similar manner how we were combining 1-bit ALUs to form 32-bit ALUs. Okay, so that's the idea, right? To kind of tame the complexity of those expressions. So we go with a 4-bit adder, right? And then we connect a bunch of those adders together and treat carry-ins of those adders in the same manner. So to make things easier, here's a diagram, right? So those are 4-bit adders, and each of them is going to have its own propagate and generate, okay? And of course, since those are 4-bit adders, instead of, for 32 bits, instead of having 32 single bit ALUs, we now only need to have 8 such ALUs, right? Because each ALU is only is now 4 bits instead of 1 bit. Okay, and then we need to build just this carry-lookahead unit, CLU, to produce the proper outputs. So those GIs and PIs are inputs, and then the outputs would be CI plus ones. So it is exactly following this approach, right? So this, okay? It just at the level of just 4 bits instead of all 31 bits. Okay, and their structure is the same, right? So this one takes PI plus 1, GI plus 1, and produces CI plus 2, and so forth. So we see that here we have not 32 bits, right? It's 16 bits for simplicity, right? And therefore, if we are with groups of 4 bits, there are kind of 4 sections, right? So the CLU is just a bunch of gates that implement those C signals. You see, there's nothing else but ands and ors. So that's the contents of this blue box. All right. So please, as an exercise, I strongly encourage that you actually build a carry-lookahead unit in one of the simulators. You can use open circuits. You can use Circuitverse. Okay, but please practice it. It's very hard to understand this until you actually build a circuit and simulate it and play with it and supply different inputs and see how those propagate signals actually generate and how they actually propagate through the circuit. And maybe Circuitverse would be even a better choice, because here you can actually look at their latencies, right? Because the next question would be, of course, what kind of latency this circuit diagram provides, right? How much of an improvement is this carry-lookahead unit over our standard ripple carry? Right, so concluding remarks before we talk about memory. So, and this is just, the overall remarks for the entire chapter 3. So bits by themselves have no inherent meaning. So if I just give you a stream of bits and ask you to find, tell me what they represent, the correct answer is, I don't know. I don't have enough information. You need to know the interpretation. Is it an integer? Is it a floating point, IEEE 754? Is it a character? If so, what encoding it uses, ASCII or something else? So by themselves, bits are just zeros and ones. They do not have any interpretation built in. It has to be supplied externally. Someone has to tell you what those bits really represent and mean. And with representation of numbers, we talked about integers, and we talked about floating point. And we see that in both cases, there is a finite range and finite precision. And we need to account for this in our programs. And that's probably one of the most useful outcomes or takeaways from this course that you hopefully adopt, is the understanding of the limitations of computer arithmetic. Okay, and you don't need to memorize the results, because hopefully now you know what is under the hood. You know why things are happening the way they are, why we have limited precision and limited range, and what happens when we go above the range, overflow, what happens when we lose precision, underflow, and how to avoid those things, or at least how to be able to detect them as you're writing your programs. All right, and so then our MIPS architecture supports arithmetic operations, of course, for signed and unsigned. Remember this U suffix that some instructions have, like load byte unsigned, and that was actually also on the test, and we're going to discuss there. And actually, it was one of the worst questions, believe it or not. I thought it was very easy, but it was actually much worse than writing MIPS code for some reason. Okay, so let's get back to this once the grades are posted. And floating point representation is somewhat is meant to represent real numbers. Of course, we cannot represent real numbers because we only have a finite number of numbers that we can store, but it's as close as we can get to representing real numbers in our current generation computer systems. So we also have bounded range and precision, so overflow and underflow can happen. And with MIPS instructions, the core instructions, and it's kind of a little soft, how exactly define core instructions, but it is in most sources and most references, they say 54 most frequently used instructions make the core, and if you look at your MIPS reference sheet, then those 54 core instructions are listed there, and they are most frequently used. The vast majority of real code uses just those instructions, and that's why those instructions are represented heavily in all their major benchmarks. So they constitute 100% of spec int benchmark and 97% of spec FP benchmark. All other instructions are a lot less common. They actually who on earth decided 54? Well, they analyzed the actual software. They looked at their instructions that are used most commonly. All right, so now let's finish up with memory, and we have about 12 minutes left, so hopefully that's going to be enough. All right, so combinational versus sequential. So combinational circuits is something that we've dealt with so far exclusively. Their output depends only on the value of the inputs. Output is a direct function of the inputs. Time doesn't matter. Anytime inputs change, output is going to change, provided that there is some latency, right? With some latency, the output will change. And that's it. Sequential circuits is something that is capable of maintaining or remembering a state, right? A state is the condition, the value that existed some time ago. And for sequential circuits, we will need a clock to synchronize and control such circuits. And we have seen what a clock is and how it can be useful. But let's look at now the memory, right? So the key here is memory. That what differentiates between the sequential and the combinational circuits. So how would you design memory? And let's start small with a single bit of memory, right? So we need to have a combinational circuit. Initially, we only have our AND or NOT gates, or whatever your functional basis might be, right? They're all equivalent to one another. And that was one of the questions on your recent homework, right? You had to show that functional bases are all equivalent. You can do everything you can with one basis that you can do with any other functional basis. So initially we start with just that. How on earth can you make this thing remember its state, right? And it turns out that yeah, I don't know how they actually came up with this idea, but I think it's a brilliant idea. It turns out I wouldn't be able to guess it probably, right? So, but it's a very bright idea. So, it turns out that we can. All right, this gate timing we already talked about. So you see how we have inputs A and B, and that with certain latency that is denoted as delta t here, and it's a standard notation. We are going to use it frequently as well. So delta t means this latency of this gate. So you see how with this latency, our gate responds to the change of inputs. So A changed from 0 to 1, and I strongly encourage that you actually draw those arrows that indicates the causal relationship, right? So you see that this is called a rising edge for obvious reasons. So you see this rising edge, A switching from 0 to 1, okay? Or usually they just draw it here, 0 here, 1 is here. This change causes this rising edge in C, because C now needs to switch from 0 to 1, okay? 0 to 1. 0 to 1. Okay, and then this is the falling edge, okay, and this is the rising edge. So this rising edge doesn't cause any changes, right? Because C is already 1, so this rising edge doesn't affect anything. Similarly, this falling edge doesn't affect anything because B is at 1. So although A switches from 1 back to 0, C is not going to switch because B of 1 maintains C of 1. So there will be no changes. That's why we draw no arrows. Arrows are only drawn when there is a change, and we want to show, which fact or which other change caused this change. All right. This falling edge of B, however, causes this, yeah, and it's more customary to draw arrows like that, right? So causes this falling edge of C, right? Because now B is switching to 0, so both inputs are 0, and that causes C to go down to 0. Okay, so remember the terminology. When something is at 1, we say it is asserted. When something is at 0, we say it is de-asserted. So only changes in C, yes, because A and B is the variables that we control, right? They are independent variables, right? Those are inputs. We change A and B. And C, it has no freedom. It's a dependent variable. C is just A plus B, right? Whatever A and B are, C has to follow. So B's rising edge doesn't cause A's falling edge. In this circuit, no. In this circuit, we don't know anything about A and B. They are only given as inputs, so we assume they are independent. Of course, if there is other circuitry, that might suggest that A and B are not independent, right? A and B are somehow dependent on each other. It might be the case that they are dependent, but in this circuit that we are looking at, A and B, we don't know anything about A and B. We assume they are independent. Yeah, C has no free will, exactly. All right, so now what we can do is we can actually use a feedback, and I cannot stress enough the importance of this word. Okay, so not in social science and politics and stuff like that, but in engineering, feedback is a fundamental, really fundamental thing. You might have heard about positive feedback and negative feedback, right? So, contrary to what name suggests, none of them is inherently worse than the other. Okay, so negative feedback is actually very good in control in control systems, right? So you actually would probably prefer a negative feedback than positive feedback, right? Positive feedback is actually bad. So feedback is an important engineering concept, and feedback is, by definition, the case when we route the output to the input. Okay, so we have the feedback here because the output C is routed to one of the inputs. So what happens when A changes from 1 to 0? So we are assuming that initially A is at 1, and we can draw our timing diagrams. Please get used to timing diagrams. Okay, they are useful. So we call this B, and so let's have A, B, B, and C. So we are told that A is initially 1, and it switches to 0. Okay. So what about B? We don't know anything about B, and that's why on timing diagrams we usually draw it like that, as both 1 and 0 in a sense. Okay. And then if A is 1, what is C? Well, obviously C is 1. It's an OR gate, right? So C is 1. All right, so now B changes to 0 from 1 to 0. Okay, and so it is now 0. Okay, so previously, well, if C is 1, we know that B is also 1. Okay, so we actually, have the, for a certain amount of time we didn't know, right? So we can we can draw it like that. But in fact, now that we've analyzed our circuit further, we know that initially we didn't know, and we draw it like that. But then we know that B is 1, C is 1, A is 1. Okay, and our circuit is in a stable state. Okay, 2 ones at inputs, 1 at the output. Okay, so then when A switches to 0, that change, does it cause any changes? No. It turns out that there are no changes, right? Because this one at B ensures that C is at 1, so C continues to be at 1, B continues to be at 1, and this change of A didn't cause any changes. Okay, so that means that our circuit is in a stable state, and it continues to be in the state due to feedback. 1 here at C ensures that, due to feedback, ensures that B is 1, and this 1 at B ensures that C is at 1. So they kind of help each other. You see how this feedback loop, it is actually called a loop. Okay, it helps the circuit maintain its state irrespective of A. If A switches from 0 to 1 or 1 to 0, it's not going to change anything. Okay, so it's a stable state, and this is a great observation, right? This is actually something that allows us to then build a memory cell. Okay. And of course, there are delays, which we can ignore here, but there are no switches here, so we're good. All right, so yeah, why don't we stop here? We are at 150, and then we continue with just a few slides, but they're extremely important about memory circuits, and next time, which is going to be on Friday. All right, so please join me for our review session tonight at 8 o'clock, and attend your review sessions tomorrow during your lab times. And with that, let me wish you good luck on your exam tomorrow. And thank you for attending this lecture. And I will see you all on Friday. Enjoy the rest of your day. Thank you, folks.